Hello and welcome back to the Oxford MAT Livestream. My name's James and I just forgot the name of this show. How are you doing? Hope everyone's all right at home. Who have we got in chat already? Oh look, it's me, an anonymous person who reminds me that you can be anonymous in chat. Someone called Shrish and Ira here. Anonymous wants this shout out. Let's read this. Oh, it's a birthday shout out. Do we do birthday shout outs? I'm not sure if we do. Happy birthday, watching at home, wherever you are, if it's your birthday. There we go. That's a generic birthday shout out that will apply to everyone and make everybody happy. Maths is on time for this. Right, okay. It's so rough, isn't it? I'm trying to decide if I can pronounce people's names. I think I'll do the birthday shout out for Saurav. There you go. Happy birthday, Saurav. Right, how's everyone's day going? Are you okay? Let's put the vote on the board. It's a vote out of 5 stars. I'm explaining it badly. You can vote for either of those things, 5 stars or 1 stars, or in between if you like. If you're having a day that is somewhere in between a 1-star day and a 5-star day, then you can choose. And I'll answer a question from chat behind. Chat is still going while that's happening, and somebody wants to know about using, they say, is it okay to use, but they're asking about using the physics submissions test, engineering test, NSAA, and Tamua math section to practice for the multiple choice questions on math. Of course it's okay. You can practice doing math questions, you can practice doing any sorts of maths questions. I'm not going to promise that those are based on the same sorts of maths. I've got no idea what the NSAA is, let me look it up. Natural Sciences Admissions Test. Huh, cool. I have no idea what sorts of maths are on that, so I'm not going to promise that the same sorts of maths, but I think there's this skill about solving tricky problems, which I mention sometimes, that if you're practicing solving tricky questions, it hardly matters where the problems are from, whether they're from a different test or just a different bit of your life or whatever. Hardly matters where the problems come from, so long as you can't solve them straight away. I think that's the only real way to practice that kind of problem solving stuff, where you don't know what to do and then you think about it and work out what you're going to do. Sort of totally different skill from actually doing the maths, right? Actually doing the maths, you practice by, I don't know, doing lots of quadratic equations or whatever, and you've probably already done that. You're probably here because you're already pretty good at that sort of bit of question. And the more interesting skill to practice, perhaps, is the one about getting ready to solve unfamiliar problems. Right, chat is having not a good day, I would say. Chat is having a kind of 3.5 day, but partly I think that might be because I said you could vote for middle options, and people have taken that perhaps as a should work for their middle, for the middle options. We will find. We will see. There you go. Okay. Right, I'm keeping one eye on the weather because there's a short update on Oxford weather. It's currently fine. I can see sunshine, but I know that very soon that's going to go away and be replaced with, well, no sunshine for ages. Good. Okay. What else are people saying in chat? Someone's doing maths, further maths and Chinese language. There's some replies in chat. Entrance requirements. Yeah. Any third subject. We'd like to see that you've got a reasonable workload, which is why we ask for an A in a third subject. Right, okay, I'm turning off the poll. How did we end up? 3.6. Not great. Let's find out if Matt can make things better. It sometimes does. You never know. Oh, it's having a thunderstorm. Right, okay, it's coming for me as well, I think. Here it comes. Jeremy wants to know about new test formats. Do you want to look at past paper computer science questions? Yeah, I think so. I think looking at past questions is a good idea. If your question is, should I look at the computer science questions because I'm a maths applicant, so previously I wouldn't have done the computer science questions, then see my previous comments about hardly matters where the questions are from, so long as you can't do them straight away. So if you have this very narrow view, then you should maybe only do maths questions that were written for mathematicians, if you're a mathematician doing a maths test. But then, on the other hand, questions 6 and 7 are often quite interesting. Question about physics, there you go. How important is math? Yeah, pretty important. Generally, if you get a good math score, then you get an interview, and if you get a bad math score, then you don't get an interview. It's not quite that simple. Can I tell the story of people offered with 20 to 30? Yeah, probably something went wrong on test day, or probably there's a reason why math was not representative of their actual ability at mathematics, which we spotted for reasons to do with the rest of their application. So we don't just look at your math score, we look at the rest of your application as well. So in each of those cases, there's probably a story. I can't tell those stories, but in each of those cases, there's probably something going on. And then they also want to know, as people often do, about people who get 90 to 100 but don't get an offer, to which I will tell you that almost all of those people are interviewed, and then the interviews also matter. Right, good, yes, it's raining everywhere. Anonymous would like to see the mug. There you go. So you can't say I don't deliver, look. It's a Tangrams mug, which is a puzzle. So the mug is also on theme for solving puzzles, right? It's not a maths puzzle, this is not on the mat, as far as I know. I don't think there's ever been a maths question about Tangrams, but the idea is it's an ancient puzzle. You have 7 pieces, a mix of triangles and squares and 1 parallelogram, and you have to make them together. Put them together to make this shape. You're given the silhouette, so you have to work out how the pieces fit together. Sort of a jigsaw puzzle with 1 set of pieces, many puzzles to make, which is why I like them. Anyway, right. Do I still think 70 is a good score? I still think 70 is a good score. I think if you get 70 on the mat, you should at least be pleased with yourself. Any advice for new sixth form students tackling advanced problem-solving questions for the first time? Yeah, Eva. Kind of almost everything I say is advice for people tackling problem-solving questions for the first time. If you want the overview stuff before we dive into this 2019 past paper, which is vintage year, 5 years ago, we're going to dive into the details of this particular past paper. I think my advice is be willing to explore stuff, even if you can't see how it's going to work out. Sometimes we just write stuff down, just see if we can play with the problem a little bit, to just do anything, which feels unfamiliar if you're used to solving problems straight away. If you're used to knowing what to do, then it can feel really weird giving yourself kind of permission to just try stuff and not know where it's going. You're kind of trusting future you in a couple of minutes' time, future you to see where this is going based on what you've just scribbled down, to kind of get halfway perhaps based on what you can currently see, and then without realising how it's going to work out, with future you to take over and solve the second half of what needs to be done based on what they can see in the future. But you have to get that halfway point. Something else I'm keen on is fluency. I mentioned before, but just being able to solve quadratic equations quickly is a good idea. Good. Right. Yeah, so people again, yeah, so is MAT similar to Tamura or easier? The only 2 things that you could be. I think MAT is much harder than Tamura, but I don't know a lot about Tamura. So yeah, neither. And then there's a question, the question chat. I think we're doing questions in chat at the moment. Question in chat. Some people scored extremely highly for MAT and weren't given an interview. That is almost always a very particular situation. And there are stories in there that I can't tell. But yeah, it is sometimes the case that people do very well on the MAT and should not be interviewed. Yeah, so no comment on particular cases, I'm sorry. It's almost certainly not you. Right, okay. How many roots? Should we add this question? Let's do a question about cubic. So polynomials, we talked a bit about in the polynomial revision session, which was, gosh, a couple of months ago now, but the episode is somewhere on this YouTube channel. Just lives down there. We did an episode about polynomials, thinking about roots of different polynomials, how many roots they've got, and it is complicated, isn't it? Because for quadratics, you know this simple rule. For higher degree polynomials, you might have to sketch them. You might have to think about where the turning points are, and it really is that complicated. So it's sort of much harder for cubics than it is for quadratics. Quadratics have one simple test for how many roots they've got. I think cubics, you can develop something like that that's much more complicated. So it's working it out at this level. Working it out for a particular cubic is tricky. Yeah, partial solutions get partial credit. So if you do have some of the idea, but it's not clear that you know entirely what's going on, you might get some of the marks. Yeah, then the mark schemes that we put on the web are not clear, I think, usually, about precisely how you get each mark. Because we're just giving you a model solution on the website. Yeah, hidden quadratics. Right, okay. Yep, so for MAT you get some sort of whiteboard stuff for writing on, which I think might be the same as the Tamura. You get stuff, whiteboard stuff for writing on. Physically. How much detail and rigor? How long is a piece of string, right? It has to be clear that you know what's going on. So you could write lots and lots of waffle with lots of detail that doesn't quite say the right reason. You know, it's about whether or not you've realised what's going on or have the right idea. Sorry, I know that's not quite. It's a bit more concrete, really. Which is good news. Good news. The main thing that people have is not a lack of detail and lack of rigour. The main problem that most people seem to have is not knowing what the answer is, which is more concrete. If you know what the answer is, don't worry too much about detail and rigour. Write enough to make it clear that you're not one of the people who doesn't know what's going on. Right, I've got quite snarky. Shall I move on to some questions? Let's move on to some questions. I'll pick out the one from the thumbnail to start off with, and then maybe we'll do some sort of voting later on. No. So BMO marking is really strange, Jeremy. Let's not talk about BMO marking. It's supposed to be if you have done about 3/4 of the work, you get about 3/4 of the marks. It's not very complicated. It helps that most of the parts on the long questions are only worth a few marks. Okay, here's a question about triangles. Some of it is hidden behind chat. Okay, so I can still see chat, but watching at home, you can't see chat. I'll try and remember that. And if I'm responding to something in chat, I will try and read it out. Okay, here's a question about a triangle. It's right angled at B. Let's try and draw the triangle. Right angled at B, A, B, C. Right angled at B, and the side lengths are positive numbers in geometric progression. As a quick reminder, a geometric progression is one with a common ratio, like this. This is what geometric progression means. I suppose if we've got 3 terms of that geometric progression, then something or other. It follows that, and then we're asked for tan of angle BAC, which is this. That's theta. We would like tan theta, which I suppose is like opposite over adjacent. So we should probably try and load up this triangle with the information that we have. We have this idea about some sort of geometric progression, and I have this idea that I want this triangle. Observation for people solving problems. This is very hard to do if you don't draw a triangle, and it's quite hard to do if you don't remind yourself what a geometric progression is. If you can't remember what a geometric progression is, that's a fluency thing. Writing it out helps me remember, oh yeah, these are just numbers, and there's a ratio. And this question is asking for a ratio as well, right? Because this is opposite over adjacent. It's the ratio between these 2 things. So, maybe I should try and work out what that ratio is. And it's a right angle triangle. So, suggestions in chat, please. How do you make progress with this question? What do you try doing? I'm not saying that the answer is going to jump out at us. These 5 options all look pretty similar to each other, so I don't think it's obvious which one it is. We could look at the options if you like. I haven't read them out yet. We could read through them, but you know, not certain which one's going on. Not certain we'll get anywhere just by looking at the options. You know, we've got to maybe also plan. Yeah. Okay. So suggestions are coming into chat. I'm going to give them a second to come through in chat. I always notice people who write the shortest things that turn up fastest in chat, which is not really how maths works, is it? Is knowing Olympiad maths a disadvantage? Oh no, hang on. Is not knowing Olympiad maths a disadvantage? I think you're fine. Olympiad uses quite a different syllabus in a way. So you don't erase stuff in. So for whiteboards for the maths, you get given quite a lot of pages of this kind of whiteboard paper stuff. You don't erase it. You can request more of it. So you get quite a lot of surface to write on. It's not the case that you just get a tiny whiteboard and have to keep rubbing it out. You get quite a lot of surface. I think it's about 10 sides of A4, so 5 pieces of A4 sized object, double-sided, for writing on to start off with, and you can request more. I think from memory, sorry. Yeah. It's not actually me. For the purposes of people in chat who needs to hear this, it's not actually me censoring chat. I have a student ambassador for that. Thanks, Callie. Callie's doing great. And the person in chat is making a point, sorry, which I will read out. In fact, I'm going to put on screen. Okay, let's put on screen. Somebody needs to hear this. I'll also read it, just because it's relevant for people watching this. You can be good at maths and still not get in, and still have a good life. And then their example of having a good life, oh, bless them, is I got S,1 in STEP after Oxford rejection. Those are good STEP grades. It's more to life than your STEP grades, of course, but I guess you're telling people that it's okay, you can get good STEP grades after being rejected from Oxford. Right, okay, somebody needs to see that. Number file uses brown paper. What was that? Did you see that at the top? The suggestion that number file uses whiteboard with brown paper, isn't it? Anyway, used to be. Right, loads of people in chat suggesting that we label the triangle, right? We have these things for the numbers, expressions for the numbers. We have a triangle. We should label things. Slight wrinkle here. I don't know whether it goes like this or whether it goes like this. There was a suggestion in chat that I draw 3 triangles, possibly for 3 different configurations of where these numbers go. I guess if you really want to get down to it, there's kind of 6 of them, right? For how you pair up these numbers in the geometric progression to the sides of the triangle. I don't know which way around it is. You might assume that the hypotenuse uses the longest side, so it's the largest term in the geometric sequence. So you can, without loss of generality, you can restrict it down to these 2 cases. I think I have 6. Cool. So we're going to get a couple of answers, I think. There's an extra wrinkle that if you overthink it, then maybe r is a number less than 1, and this geometric progression is actually getting smaller. But that turns out to give you the same solutions, because for any geometric sequence, if you know that 3 numbers are in geometric sequence, you can also relabel them the other way round and still get a geometric sequence. That's just a fact about geometric sequences, that if 1, 2, 3 is a geometric sequence. Stupid example, 1, 2, 3. 1, 2, 4 is a geometric sequence, but so is 4, 2, 1 with the opposite common ratio getting smaller instead of getting larger. 1 over r, if you like. That's just a fact about geometric progressions, which doesn't really give us different cases for these things. There's still a largest term, which should be on the hypotenuse. Anyway, these are the 2 cases. In this case, tan theta is r, and in this case it's 1 over r. But we have to work out r, and there's lots of suggestions in chat about using Pythagoras, which is a good idea. I like Pythagoras because we've got this right angle triangle, of course. So if you write out Pythagoras, then for either diagram, you get this statement, which looks like a high degree polynomial, but we're not too bothered because we can divide both sides by a squared. We're pretty sure these numbers are not 0, so we'll get this. That's a degree 4 polynomial, but I think you can spot what we're going to do next. We've got all these square roots around, right? We're definitely going to start thinking about square roots of things. So we'll get some solutions to this equation somehow. There are some suggestions in chat that the hypotenuse might be a. That's in the case that a is secretly the largest of these 3 numbers if they're getting smaller. And this turns out to be exactly the same as one of those cases with. It's got 1 over r instead of r, so it's still capturing this dichotomy, this kind of choice between 2 things. It's got 1 over r instead of r, so this is kind of included. Nothing wrong with it. If you want to write this out as well, you will get the same equation with 1 over r instead of r. But as it stands, we're going to write down, at some point, we're going to make sure that we have solution or 1 over that solution. Okay, yep, scale it and use a equals 1, that's a good suggestion. Yeah, just we're interested in a ratio, so who cares about the actual numbers? Fair enough. I like to think of it as that the a's cancelling out at this stage, but I guess that's Pythagoras telling me that you can scale right angle triangles as well. Yes. Okay, yeah. People still talking about this dichotomy. Somebody wants me to comment on whether maths got harder, and somebody else wants to comment about percentiles. Both of these questions are secretly about the number of applicants, which has gone up over the last 10, 15 years. So these trends shouldn't really concern you in some sense, but So we're just going to apply and do the best that you can with maths questions. We can use the quadratic formula. In fact, let's use the quadratic formula. So if we write u is r squared like this, then we get something like 1 plus u equals u squared, which is a quadratic equation. So now I'm happy because I get something like this. B squared minus 4. I feel like I've solved this quadratic before in my life, but never mind. We get 2 roots, and of course this was u equals r squared. I'm trying to get a solution for r. I would like r and 1 over r, so I'm going to get quite a lot of roots, aren't I? Because I'll get 2 things here, and then I'll do the square root, so plus or minus sign up there as well. So now I've got 4 things, and then I'll write down that or 1 over that. So I'll get 8 things at the end. And none of the options have 8 options in, so now I'm worried. Help me out, chat, what's going on? Oh yeah, golden ratio. For fans of the golden ratio, we have hit the golden ratio, 1 plus root 5 over 2. Also 1 minus root 5 over 2, but I'm less interested in that one. Why am I less interested in that one? Yeah, there's some positive numbers, and the person with the step grades, that's how I'm going to refer to them. The person with the step grades has clarified that they didn't mean that step was good life. That was just me teasing them. Sorry, I'm teasing because they've set their username as James. Please don't censor. They're going to get a little bit teased for that. Life is not what a given uni will mean, but how you apply yourself, come what may. That's nice. How can it be negative if it's a triangle? Yeah, don't go negative. Also, don't go negative because this is a square number. Well, a square of a real number, sorry. It's a positive or 0 quantity. Oh, I typed myself in a knot there. What a terrible way of saying this is non-negative. It's just non-negative. Look at it. Here it is. It's non-negative. So we want r squared. So u is 1 plus root 5 over 2. I seem to be adopting a slight slant. So to my writing, sorry, we'll go back like this. Then we have r. So I do think getting there. But actually we don't want this plus minus sign either, do we? Because the sides of the triangle are positive. So sides of the triangle are positive. So I'm going to keep going down. Here we go. Sides of triangle are positive. It's funny really. 1 minus 2, 4 is a geometric sequence. And it would square to the same stuff if you put it in Pythagoras. So this thing is going to keep happening to us, I think, if we do problems like this where you have squaring going on. And finally, we remember that tan theta could be r or 1 over r, not because of the square roots really, but just because of how we don't know which way around the triangle is. We don't know which way around a and c are. So it's this or that. And this doesn't quite match the options in the question, which look a little bit tidier. But then you remember that you can simplify this one. I think probably motivated by the options in the question. You write out something like this: to multiply top and bottom by root 5 minus 1, which I've picked because that lets me do difference of 2 squares down there. I would love to do difference of 2 squares because then, root 5, the square of root 5, brilliant. It's 5. Take away 1 is 4. So this starts to look a lot like one of the other options, root 5 minus 1 over 2. Which is, there it is over here. I get this root 5, and I get this root other thing. Good. So I think we're picking this as C. Cool. Okay. How are we doing? I think we're doing all right. Let's turn chat back on. I think we got an answer. There were some quadratics along the way. Maybe I wouldn't see those coming. Just thinking about general problem-solving skills again. We had to solve an equation, but you get good at solving equations if you solve some equations. This one's secretly a quadratic equation in disguise, but I've seen something like that before. You have to be quite careful near the end to remember the things in the question where we started, that these things are positive real numbers, and there was this confusion about which way around the triangle was. And that's normal, I think. It's sort of like checking your answer, I suppose, to start off exploring and make sure that after you've done your exploring, you come back to the place you started. That's not a good metaphor, is it? Make sure that the answer you end up with matches the question that you were originally trying to do. So suggestions in chat. Anonymous at the top there, I think, is suggesting that you just check which of the options are two things that multiply to give 1, which is sneaky, really. Do we put any tricks in there to make that go wrong? Not sure we did. Option E is a bit interesting. Option E might trick you a bit. Option B, what does that give you? 3 minus 1. Try to work out if we. Yeah, option B, I think they multiply to give 1 as well, but I'm not sure. Sounds too good. Sounds too good to be true. Big square roots. 3 take away 1 is 2. Over 4. No, they don't. Yeah, okay. I like that as an attack. Yeah, okay. Once you've decided that it's this, check the options. Multiple choice questions have a little bit of weakness, don't they? And the question there: if my school does not offer further maths, do I need to make Oxford aware of this? I recommend it if you can, so that we know, so that the tutors and everyone who looks at your application knows for sure when they see your application that the reason you don't have further maths is because it wasn't offered at your school. You could put that in your application, or you could email the college that you're applying to at Oxford, and maybe other universities you're applying to as well, if they will take it into consideration too. Yeah, it does make a bit of a difference, doesn't it? Whether if further maths was not offered to you, then that's not your fault. Yeah, okay. What's been my favourite math question? I'm just going to pick my first one, right? I'm going to pick the one from last year. There you go, 2018. Well, great stuff. No, my favourite one's probably the one with logarithms in from 2021, but we haven't got there yet. That was a long question. We haven't got there yet. That's 2 weeks away. I'll just let you know my favourite math question when we get there. Okay, Aidan wants to know about interviews. There's about 100 people doing interviews. Loads of people. Most of the people involved in teaching for tutorials in Oxford get involved in interviews. Also, a bunch of other people. Some of our graduate students, after they've done some training, help out with interviews. Lots of stuff. Right, I'm going to add a multiple choice question to let us know which question next. So the options are going to be, out of everything in 2019, oh my goodness, I have to type these one at a time. Oh, this is going to be slightly slow. Kill time slightly. You can put in chat if you like, if you want to look at a particular question, which question you would like to look at, or you can wait for this poll to appear, which will turn up in just a second once I type all of the numbers from 1 to 7. Oh my goodness, here we go. Okay, question 7, good. Do I need to set any rules? Let's find out. Poll settings. Poll results are visible. Multiple options. There is no correct answer. You can select up to 16 of them. Start. Does that do it? There we go. Voting. Right, there's some chat in there as well. Question 5 requested, and also has some votes. What job can a mathematician do despite teacher? Yeah. Lots of our graduates go on to work in software and finance and consultancy, and then a whole variety of different things. The pie chart breaks down really quickly. Lots of our grads are interested in doing very specific things, some of which they discovered during the course, what they want to do afterwards. Maybe they've done an internship, or maybe they've just seen something they're really interested in. There's no sort of specific career that you have to go and do after you do maths. You just have to be a teacher. So if you want to, there's big demand for maths teachers in the UK. Yes. Right. And then anonymous. What's the question? Oh, how much time management for Matt? No, hang on. Is it okay to? Oh yeah, hang on. Is it okay to ask questions if we don't understand? Yeah, please do. Please ask questions. And I'm sorry I missed that in chat. Somebody asked if they could ask questions. Which, yeah, it's good. Okay, looks like 4 and 5 are winning at the moment, so I'll go and start them on screen so that people can form an opinion. There's something about distances to subsets, and there's something about counting subsets. Both these questions got the word subset in. This one doesn't say subset, but it is about subsets. Jeremy wants to ask a specific thing about question 4, part 6. Can I, if we do question 4, which is looking very likely that we'll do question 4, when we get to part 6, that's probably the right moment. Otherwise, I've got to jump in, and there's a chance that I'll forget how question 4 works if I do it out of order. Okay. Oh, can you ask, and maybe they're asking about interviews, because we were talking about interviews. Yes. If you don't understand something during an interview, please do say, please do ask. The interviewers are there to help, and we're not mind readers. We want to see you solve questions, and you can only really do that if you understand the question that's being asked. So do say, especially if you think that we've used a word that isn't the word you were taught in school, which can happen if you're studying somewhere else. We say a strange word, then you should check. Or even if you're in the UK and you just want to check what a word means, that's also fine. Okay, so Anonymous says, I know you're a tutor at New College. I do some tutorials at New College where it seems like maths, computer science and joint applicants compared against each other, bracket 8, close bracket. Am I disadvantaged if I apply to New? So what they're saying is that New College has got quite a few students and we take the best students. Is it a problem? No, I think I don't really see how that's a disadvantage. Sorry. We take loads of students. We've got other courses too, like French. A levels are best. It doesn't matter. George, it's fine. Whatever you're doing as your third A level is fine, unless it's general studies, and no one's done general studies for years, so I think you're fine. Right, questions 4 and 5 have tied this poll, which is exciting. Does anyone want to break that tie? Just to determine what I'm doing first. Give you a second. Nope. Okay, good. Right, I'm choosing. We're doing 4, and then we'll do 5. Okay, that's our set. 5:30, so I'll try and do 20 minutes on each. Let's see how that goes. Anything else in chat that I want to do? Oh, someone just said 5 in chat, just as we got there. There's a question about the 2 multiple choice questions. I think they're mixed up. There are 25 multiple choice questions, and there are 2 long questions, and the syllabus is on the website. And lots of people seem worried that this year everyone's doing the same questions, so maybe it will be about a robot or something. I just want to reassure people that whether or not it's about a robot, it's using maths, and we've checked that the questions that we're asking are appropriate for maths applicants and appropriate for computer science applicants. And really, for some fast questions, it really is whether or not the question has a robot in. Not even consistently that the robot's in computer science questions, but for sometimes you sort of think you could remove the robot and it would be obviously just a maths question. Someone emailed me to ask me if questions were going to be about maths or logic, and I thought that was a little bit amusing because lots of questions are about both. Some people think maths is a sort of logic, some people think logic is a sort of maths. Maybe we shouldn't do that right now. This is a circle. I've drawn a circle. What was the question? For a given point AB, we want to find the unique point of this, and I suppose it's a filled-in circle because it's x squared plus y squared less than or equal to 1. So that represents some sort of coloured-in circle. And now it looks like it has no edge, which I don't like. There we go, including the edge. For a given point AB, I'll need to consider separately the cases where a squared plus b squared is greater than 1. That means something like the point is outside the circle, in which case the closest point within the circle, or the edge, to that point is the point right here, on the outside of the circle. You imagine moving around the circle, you want to get as close as possible to that black spot, you go over here, which is something like a point that's got distance 1 away from the origin and is in the same direction as the direction of the point AB. So it's something like AB divided by root a squared plus b squared. I'm dividing by the length of that vector. We've done this before on the live stream, I think. There's a trick to write down something that has the correct length. A comma b divided by root a squared plus b squared. That's if it's outside the circle. If it's inside the circle, then the closest point to it is just the point itself. It's inside the circle, inside the circle. Okay. Do we submit in time limit? Yeah, I think if you hit the time limit, it submits. Yes. The alternative would be mad, right? The alternative would be that it doesn't submit because you ran out of time. No, that would be stupid. I'll double check, but I've now said on stream that one of the alternatives is stupid, so I don't think you should worry about that. The students in Oxford live in college accommodation in first year. We don't use the phrase boarding houses. I think boarding houses make me think of not great accommodation. College accommodation is pretty good. Individual rooms. You can find out more on the college's websites and on General Oxford website about how accommodation works in Oxford. Oh, subset. So I mean some of the points. So if you've got a set for maybe all of the points in the plane, a subset is just some of those. So here I've been thinking about the whole plane and the subset S, which is some of the points inside this blue circle. Good. Okay. Part 2 of this question wants us to do kind of the opposite, to describe a subset and a point AB such that there is no point of S nearest to AB. There's no point that's nearest, which sounds impossible when you first hear it because, well, we just did some calculations, right, to find the closest point in 2 different cases, closest point to a given point. But after a while, maybe play around with some sets. So maybe my first idea is something like I could try and trick it so that all the points are really far away. But then I realised that no, well, so the point that's closest to AB would just be the point on the edge that's closest to AB. That's kind of my silly justification to start off with. And then after a lot more thinking, I think, well, what if I get rid of the edge? So what if I get rid of the edge by taking like this circle and removing the edge? Well then, underneath chat, sorry, we're going away again, chat. Underneath this, if I take away the edge, then this point, which I said was on the edge of the circle, doesn't exist. It's not in the set S, I suppose. So there is no point inside this circle, which is x squared plus y squared, strictly less than 1. There is no point in this set, which is actually the closest to that point. For any point inside the circle, there's another one. So question mark this one? No, because there's another one that's even closer to that. You can keep moving outwards. So the kind of key idea is maybe to get rid of the edges. There are other solutions that work. Sophie says if you just have 1 point, I think that then it would be the closest. If you have no points though, if S is the empty set, and this is the set with no points in it, then sure, there is no point of S nearest to A, comma B, because there is no point in S. I suppose Sophie's question is something like, if there's only 1 point, does it really count as the nearest because there's nothing to compare it against? And I think maybe it is the nearest in the sense that there's no point that's closer if there's 1 point in S. Anna took this to mean all the points at equal distance, which is a solution to part 3, where if you have, so the most common thing that people wrote for this question was a circle that's only edge, having picked up a kind of circle theme for their solutions so far. So if I take this circle and remove the interior to just have kind of the ring x squared plus y squared equals 1, and I consider a point right in the middle, then there is more than 1 point of S nearest to A, comma B. And more than 1 that's nearest. I think there's a definition. There's something about nearest up here. No, we just say nearest. Many such points are unique such point or no such point. I suppose the wording of the question makes it kind of clear that we're considering a tie to be 2 points that are both the nearest to A, comma B. The other first thing I thought of when I tried this question. The first thing I drew was this kind of weird C-shaped thing, so that there were two kind of totally different points over here and over here or something that were closest to the point A, B, so reaching in from two different directions. I don't know why I thought of that. It was a lot of effort to think of that. I could have just plonked something in the middle of a circle or something. Yeah, so then part two, the difficulty of marking part two in 2019, of course, was that people defined the empty set in lots of really strange ways. Like somebody in chat has just said x squared plus y squared less than 0, which has no solutions. So they mean the empty set. These sets are the same. That is just the empty set. But then you get this very tricky problem that people will say, well, what if it's the set of all, and then define some problem with no solutions? And you think, oh gosh, I've got to work out if that problem's got no solutions. Or maybe more accurately, I wish the question didn't say without further justification in hindsight, but there you go. This question says without further justification. So there we go. Guess it could be quite hard to prove your particular set. Anyway, a spiral that limits into the point, because then there would be no point that's closest to the middle. I like that suggestion. Thank you, Jeremy, in chat. Like this, going inwards towards the middle. So then you can get closer and closer, but you can never be definitively nearest, in the sense that there isn't a nearer point. Are you always allowed to add and remove lines from diagrams on the map? In your working out, you can do whatever you like. In your working out, you can draw your own diagrams. Okay. This question, there's some discussion about the wording of the question in chat as well. So also a different solution to this one is to take not just the circle, but also everything outside the circle. Okay, I can't tell if we're having fun. I sort of think from the comments in chat that we might not be having fun because of, well, maybe this question needs a definition of nearest. It keeps using this word. Maybe it needs a definition of nearest. And the idea that you can have more than one point. So I guess it does say that up here. Many such points are unique or no such point. Right, anyway, then the question gets back to something that looks a bit more like maths you do in school, right? Which is to say, please find me the distance between these 2 points. So you have this point on the line, x comma mx plus c, which is a little bit strange. You might write x comma y for a point, but we know y is equal to this expression. We'd like the distance, which is something like, take the difference between the x coordinates, take the difference between the y coordinates, square them, add them, and take the square root. This is Pythagoras again, isn't it? So that's my expression, and my distance, and then I'd like to talk about the point that's closest. So maybe I recognise that inside the brackets here, there's a quadratic equation. And that quadratic has a unique minimum. There's maybe some justification, minimum. Oh gosh, I'll just put a big squiggle and you can assume that I've spelled minimum correctly. There's maybe some justification here to say this is the sort of quadratic that has a unique minimum, happy quadratic, one that bends upwards, which is not too hard. But then if that's called unique minimum, then there's only one point that's nearest. Yeah, you're trying to minimize the distance. This is nice because you can actually do the calculation. I think you can actually work out where the point is as well. You know quite a lot about quadratics, including where their turning points are. You can work that out. It's not too bad. The question doesn't ask you to, but you could calculate it. It's not too painful to do that sum. I'm not going to do it on the board now. You can also do some geometry. If you would rather do some geometry, so you can do some stuff there. We're getting towards part 6, which I know that at least one person wants to ask questions about. But first we have to talk about part 5. Part 5 says there's some subset S, and here's some information that we're given. So this question is again twisting it around again, so that just now we were getting pretty close to working out the nearest point in S to a general point AB, and now we're being told somebody else has done that calculation or something. Here's their answer. What was the question? Or something like that. Because that's not what the question says, right? The question says, here's a subset. No, for some subset S, the nearest point of S to A comma B is this. Describe the subset S. And this is tough. I think you have to realise that the thing that was a breakthrough for me when I was thinking about this question, I don't know, maybe you realise this straight away, but it took me a long time, which is that these points are actually in S. I'll write it on the board. For all A and B. And then I should ask things like, where are they? It took me so long to work out that these points, we're being told about this, the nearest point of S, but forgetting about nearest for a while, we're being told it's in S. As AB moves around, we're being told information that's revealing something about where this subset S is. And of course there might be other points, like how for the circle example, as you move AB around outside the circle, you only get to see the outside of the circle as you move AB around until you move the point AB inside the circle, at which point you discover, aha, now the nearest point is that point itself. Well, I suppose this is going to discover all of the points that are in S, because if a particular point is in S, then the nearest point to that is itself, if it's in S. So everything in S gets visualized at some point for some values of A and B, set A and B to be the coordinates of this particular point. Every point in S gets visualized by this equation at some point. So maybe I can do more precisely than this. It contains like exactly the points that are in S if you vary A and B. And more than that, you can write down some equation that relates together these coordinates. They're not just random expressions of A and B, you can find a link between them. Yeah, so S is just changing in each part. I think there's some text up here. In this question, we will consider subsets S. And at first we're told that it's the disk, and then we're asked to describe an example of a subset. Later on, they say let S denote. It's different each time. Otherwise, this is easy, right? If it's still the circle, then this is easy. Yeah. So there's a straight line going on here somewhere, because for each of these points, so for each of these points, I can see A plus 2B over here, and I can see 2A plus 4B here. So I know something like, oh gosh, how do I unpack that? So this bit of X. So X is A plus 2B minus 2 over 5, and Y is 2A plus 4B plus 1 over 5. Maybe surprisingly, I can eliminate A and B by rearranging this to say something like 5x plus 2 all times 2 is the same thing as 5y minus 1. So I'm trying to rearrange to get this kind of A plus 2b expression that appears in both of them. And over here I have to double this one up so that I get 2a plus 4b to compare it with the one on the right, which gives me something like 10x plus 4 is 5y minus 1, which is not too bad. I can work with that. That's the equation of a line. It's a straight line. I'm not certain I've got the correct straight line, but you know, I'm getting there. So 2x, and then there's is that another 5 plus 1 or something? Check my answer, minus 4/5. So if I double all of this stuff, I get minus 4/5, and then adding 1 means adding on 5/5, which brings me up to plus 1/5. We are neglecting to draw a diagram, but I don't really know what diagram to draw because AB could be anything. This says for any point AB, so AB could be anywhere. I'm now happy to draw a diagram of this sort of straight line. Y is 2x plus 1. What we are being told is that as AB moves around, let's group that and move it around. As AB moves around, you see different points in the set S, which are the nearest point to AB, including some where AB is actually in S, in which case the nearest point to AB is AB itself. I guess that sometimes happens. yeah, I'm not going to overthink that. I'm not going to solve the equations to work out when that happens. It's when AB lies on the line. It's when B is 2A plus 1. I did overthink it. And sometimes you get sort of this tells you this equation relating together A's and B's. Like shining a light around and finding, you can just see a little bit of it for each value of AB. But our final answer here is not in terms of A and B, because A and B could be anything. They could be at any point in the plane as you move AB around. So that's not part of our solution. That's sort of dummy variables that at some point, as AB moves around, you visualize different parts of the set, including all the points in the set. Whenever AB happens to shine a light on that point exactly, and other occasions too. Yeah, so S is independent. S is not really a function of A and B, because A and B aren't fixed numbers. It sort of wouldn't mean anything to say that S was AX plus B, or line perpendicular to a particular point, because A and B could be anything. So it says for some subset S, for any point AB, any point, not a particular point, any point, the nearest points of S to AB. So it's trying to fix the subset S, well, telling you there's a fixed subset S, but the point AB can vary. That is really fiddly. The question's got quite precise language going on. Okay. Part 6 wants to try and go back to this idea about whether or not there's a unique nearest point. We're given a property. Say that S has the property that for any 2 points P and Q, so maybe S is some sort of blobby circle thing, and there are 2 points P and Q. For any 2 points P and Q in S, the line segment PQ is also in S. That's the line segment between P and Q. Show that for a given point AB, there cannot be 2 distinct points of S which are nearest to AB. So this is going to be a proof where we say something like, suppose that there were 2 distinct points. Oh no, nonsense follows as a result. That's just my guess of how this is going to go. We can start trying to draw things with P's and Q's in to talk about this. If you think about distances. Wait, I've missed a bunch of chat messages. Anonymous wants to know about the 2 longer questions, how many marks they're worth. 15 marks for each of the long questions. Check the MAT page for more details about the format. Could we have equated A to the x coordinate of S and B to the y coordinate, and then seen that the relationship is linear? Yeah, that's something like, suppose that AB is in S. If AB is in S, if AB is in S, then this has to describe the point itself, and that gives you some relationship between A and B. Yeah, that works. I think it's the same relationship. I hope it's the same relationship. Yes, it is. Good. And these are kind of consistent equations, which is interesting. I suppose this thing has to be consistent. Right. Yes, the line from AB to the line is perpendicular to the line when the I see. Okay. Perpendicular to the line when the distance is minimum. Oh, so maybe we can use this. I see what you're saying. This is a suggestion in chat that probably the people who wanted me to draw a diagram wanted me to draw this diagram or something to say, as you move the point in S through maybe points like this, this is the nearest one. So think about the gradient of this bit, and then you get the gradient of the line. If you know it's a line, then sure you can work out the gradient of the line like this. Or the gradient of like other points in there. Not sure what we're working out, what we're assuming about S, but yeah, you can do stuff like that, can't you? You can work out the gradient of this bit, M question mark, and then you can work out the gradient of the other bit. So it should be -1/2 if that's all worked out. So the gradient of this line, because it is a line, the gradient of the line will be 2. Yeah, it seems plausible. We don't know from the start of the question that it is a straight line, but Turns out it is. Good. Okay. So part 6 then. Jeremy in chat, who wanted to talk about part 6, is one of the people who voted for question 4, I think. I don't know, to be clear. I don't get reports of the voting. Consider the circle centre. As I said it, I realised that's the sort of thing that's going to scare people. Consider the circle centred AB which passes through P and Q. Yeah, it's got great geometry. I like it. Suppose they're the same distance. Yep. Draw a circle with centre AB, passes through P and Q, and then this segment's a chord and contains points closer. Yes. Okay. And you'll use the fact that the line segment is in S. Yes. Okay. I like it. Let's do something like that. So this is going to look a bit ridiculous, but suppose P and Q are two distinct points of S, which are both nearest. And depending how you feel about the word nearest, maybe you'd prefer some sort of definition like maximally close or something, or minimally close might be more accurate, I suppose, like minimally distanced from AB. There's nothing closer, which obviously my diagram doesn't do, because look at all this empty space. Could get way closer to the point AB. But let's suppose, and then the suggestion in chat from Jeremy is draw a circle, but I could also imagine drawing a triangle. I could also imagine doing some sort of straight line science. The circle that you might imagine drawing is centered on AB and goes through P and Q. Oh, what a great circle. There we go. Yes. Didn't really go through P and Q. Can fix that. There we go. The circle you might draw is this one. Circles are nice because everything's equal distance on a circle, as you can see from this diagram. Gosh, that's a bad circle. I'm not having another go. So Jeremy's argument in chat is that the points in between are obviously closer. We know they're in S because this statement says the line segment PQ, there is a chord of the circle, is also in S, so some of those are clearly closer. The midpoint is closer. The triangle that you might draw looks like this. You might draw this isosceles triangle with 2 points the same, and then you might drop a perpendicular down the middle. Say the midpoint is also in S because you told me the line segment is also in S. It's got that property. That's a property of the set, which is nice. And then you might point at that and say Pythagoras noises, right? More specifically, you might use the word hypotenuse. You might write down some square numbers, some expressions that are square, and talk about this one being kind of smaller. And then thirdly, so that's green over here. Thirdly, you might draw a line. You might draw this whole line between P and Q, and you might say, well, in part 4, we said that distance is a unique minimum, and now we're saying it's got 2, so that's interesting. We said it's quadratic. Okay, it's a square root of a quadratic. The distance is the square root of a quadratic. Can't have 2 equal values, and then I suppose without being smaller, without smaller in between. Using your advanced knowledge of quadratics, which you know loads of stuff about quadratics. In the circle, PQ is a chord, and it's unlikely to be a diameter. I suppose it could be a diameter. A diameter is a special sort of chord. And there's some discussion. If there is a gap of the subset between P and Q, aha! If there's a gap, then, so if some of these points are not in S, then the argument would completely fall apart. The things that we're saying wouldn't be true at all if that subset, if that line segment between P and Q isn't in the subset, then none of this works. The thing we're relying on is very much this property here. For any 2 points, we're supposing that S has the property that for any 2 points P and Q in S, the line segment PQ is also in S, which is great news. Stuff in between. So P and Q, yeah. So this is proof by contradiction, which is a sort of arguing technique that some people learn in school and some people just kind of pick up because it's a sort of arguing technique you can just do outside of maths, where you suppose that the person you're arguing with is right and show that complete nonsense would follow as a result. It's just something you can do in an argument. If that were true, then terrible. And that's what we're doing here. We're saying, well, if there were two distinct points which were both nearest, then nonsense would follow. We would find a third point in the middle somewhere, because you know line segments there. We'd find a third point in the middle that's even closer, which is nonsense. Nearest and then an even closer, that's not how nearest works. That's the one thing that nearest means, is that there isn't a nearer point. So nonsense. Therefore, this never happens. So you can't have two distinct points which are nearest, and the points would have to be the same. That this choice of P and Q, those two distinct points which are both nearest, doesn't happen, and instead P and Q would be must be the same, unique closest point. My diagram's not very good, is it? Because this sausage shape that I've drawn for S, it has got a kind of bit in here where P and Q aren't like that. I drew a bad picture for S. I'm supposed to draw something that where the line segment is always inside. I'm going to quickly fix that. There we go. Otherwise you'll pick P and Q to be up here somewhere, so the midpoint is not in S. Totally different problem. Okay, good. We've hit 6 o'clock. Remember, if you've been looking at a screen for the last hour, to sometimes look away from the screen. I'm going to drink some water. Right, and I think it's time to talk about question 5, because there were lots of votes for that, and there is someone in chat saying 1i, which I do see. Yeah, 1i. Oh, I can do 1i really quickly. Let's do 1i really quickly. Pop, there you go. The resolution comes not immediately. 1i really quickly, because you asked nicely. The main thing that you realise here is that we should try and sketch x 2 to the x. Don't forget, don't worry about the y's right now. But if we try and sketch x 2 to the x, you can draw 2 to the x. X times 2 to the x, well, it starts at 0, because when x is 0, this thing is 0, and then it's just going to get larger and larger, isn't it? X is getting larger and larger. 2 to the x is getting larger and larger. Once x gets past 1 or something, where, for smaller than 1, I guess it's making this thing smaller than it would have been if there wasn't an x there. It's not really contributing enormous magnitude. But then when x becomes a bit larger than 1, this is even larger than 2 to the x. This is really huge, is what I'm saying. Once you've realised that this is really huge, x is positive, so I'm only drawing this side of the picture. Once you've realised that this is really huge, you realise that you're being asked about two numbers that have the same value. So, I guess you want this thing only happens. Maybe the x and y is confusing, and maybe it'd be nicer if it said, I don't know, let's rewrite the question with a's and b's in. Is this nicer? Because then I can talk about them being values, right? A 2 to the a equals b 2 to the b. So then you're thinking about a and b being just two numbers that you can stick into this function. Maybe that's nicer if I change the letters of the alphabet around here. Got to remember the options should be in a's and b's now. But then it's pretty obvious that these things are not going to be equal. The one with the larger value is going to give you a larger output. So this is ridiculous. So it's like only if a equals b, oh no. A is less than b, so this never happens, which is kind of nice. Right, okay. Oh, they actually said J. Right, this is why you take a little break. If you've been looking at the screen for an hour and you can't tell apart different letters of the alphabet, then here we go. Right, I'm going to go and do 5 and then come back to J. I did such a good job with I though, didn't I? Oh, wasn't that nice? Nobody asked for that. Let's check the vote quickly. Is it true that nobody asked for this? No, that's the how's your day vote. Nobody asked for this. Yeah, 5% of people, I think that's one person, wanted me to do that. I hope they're happy. And they may have voted for everything. Okay, good. Right. Yeah, so someone in chat is differentiating x e to the x. You are actually not required to be able to, you're not expected to be able to differentiate it. I think it's obviously increasing though, isn't it? Right, question 5, here we go. you've seen how I run these now. I'm going to go through part by part, and if nobody stops me, then I'm just going to talk about it piece by piece. A-levels. If you're applying this year, you take MAT this year. Sorry, just while you're thinking about question 5, here's the setup. I'll let you read the setup. Quick things in chat. If you take a gap year, you're applying the year that you take the MAT the year that you apply on UCAS. Existing A-level grades, if you've got them and they're recent, then go for it. For mature students who are over 21, when this, of course, we say we look at recent 3 years. I guess for most gap year candidates, it includes all of their A-levels. So it would be really unusual for us to ask you to reset A-levels if you've already got the grades very recently. 2 long questions, the same length as the longer questions the previous year. They're still worth 15 marks. Okay, right, question 5, let's go. This question is about counting the number of ways of partitioning a set of n elements into subsets. Oh, there's that word again. So we're splitting them up into these collections of the elements, each with at least 2 and at most n elements. Nk are integers. We're going to say f. Nk is the number of ways to partition this. For example, f52 is 10 because, yeah, here are some allowable partitions. Splitting up, so partition means splitting up the elements of this set 1, 2, 3, 4, 5 to split them up. So these separate ones, there are 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm showing you how to split up the numbers from 1 to 5 into subsets, each of which contains at least 2 elements. And there are 2 subsets because this number here is 2. Okay. Right, so first part of the question is to check that you've understood the notation and the question statement and this thing about two elements. And the idea is that this is no, you need loads of elements. You need at least 2k elements if each subset contains 2. At least 2, I suppose. You know, there are k subsets, each has to contain at least 2 elements. This inequality tells me that n is small, it's smaller than 2k. So if n is smaller than 2k, then there's no ways to do this. There's not enough elements to go around. Which, I know when I say that, it just sounds like I'm telling you the answer, but this question really is just here to check that you've understood so many different objects, right? You're getting marks here for understanding that f is about counting the number of ways, which is why it could be 0 if there are no ways to do it. To link those together is the idea that this is no ways. I should just write no way. It's impossible. You're understanding what the roles of k and n are, what these mean for the actual problem, in terms of like these definitions up here about what goes into f. What are the inputs? And crucially, you're trying to understand this number 2, which is this restriction in the question about how many elements you can put in each subset, which is going to matter quite a lot later on. So this is kind of not much question in terms of actually doing stuff with the objects. We're checking that when you double k, you get 2k. We're not doing much algebra here, but checking to understand the parts of this. Jeremy's already seen this. So Jeremy, if you've already seen me talk about a question, then there's not much value in seeing me talk about it again, but maybe people get involved in chat. They're still talking about math questions in general. At the start of year 12, no, because you don't know the content yet. If you're at the start of year 12, like this person says they are, then probably you haven't seen enough A-level maths yet. But for the questions like this one, which don't use very much A-level maths, maybe you can just join in. You're probably with us so far, right? This thing says you've got to have 2 in each thing, and you haven't got enough of them. You're probably with us for the next couple of parts as well. Let's find out. Maybe all of it. Maybe you can do all of this question at the start of year 12. I might have spoken too harshly. Cool. Okay. So Fn1 says that we're going to take n elements and put them in one subset. So all in one subset, and there's only one way to do that. And then if you think a tiny bit more, you remember that, oh, if n is greater than or equal to 2. If there's only one element, then k is smaller. If there's only one element, then k is larger than n over 2, because 1 is larger than a half. Why is 1 larger than a half? Oh, because 2 is greater than, yeah, never mind. 1 is greater than a half, so f11 is 0. So this thing is 1 almost always, but if n is 1, then, oops, surprise, f11 is actually 0. Okay, yeah, right, good. Okay, we've got some values. We've got this thing is sometimes 0, sometimes 1, sometimes 0 again. Let's find out some interesting values. So we know it's sometimes 10, f52, if you're putting 5 elements into 2 subsets. We're doing very small problems here, time to do a big problem. When we're making a partition of the elements up to n plus 1, the elements go from 1 to n plus 1, or n plus 1 of them. Putting them into subsets of at least 2 elements, we can either pair n plus 1 with just one other element, leaving n minus 1 elements to deal with, I guess, later, or we can take this allowable partition of these things and chuck in n plus 1 as an additional element in one of those subsets, or making an even larger subset of size, exciting 3 or more. So the rule here is going to be that n plus 1k, which is the number of ways total to make partitions into k partitions with n plus 1 elements, that's going to be related to, I think, just the sum of these, or something like that. Something like those 2 different cases that I should add together. I should think really carefully about what those cases are. I think it's going to be the sum of 2 terms for these 2 different cases. We've seen problems like this before on the live stream, where if you're counting something, you might be counting mutually exclusive cases, and that's quite a powerful technique when you're counting to break the problem down into separate parts. This question actually tells us how to break it down. It gives us these 2 bullet points for 2 mutually exclusive things that might happen. The idea is that you go and solve these mutually exclusive cases and then add together the number of ways total. Because they're mutually exclusive, you don't get any overlap and you don't miss any terms. When I say mutually exclusive, maybe that makes people think of statistics or probability or something, but it's just a kind of phrase about things with no overlap. Okay, let's think carefully about what's going on in the first case, first subproblem. This is the idea that n plus 1 is paired with another element, like maybe 2. So up here, n plus 1 is our largest number. Up here, I think it's the number 5. Let's try and highlight those. Can I highlight? Worst highlighter. Paired with one element, so maybe 2, and then the others are paired. Others are partitioned. So the idea here is, I suppose, there are 2 steps. You can pair n plus 1 with any of the elements. So you have a choice here that's marked choices. You've got a choice here about what you do, and then you have choices about how to do the partition for the rest of them. And here they're not mutually exclusive. It's not the case that you choose what to do with the n plus 1, pairing it with a single item, and then you don't have to do anything else, you're done. You have to make both choices, and they don't affect each other. They're independent. And in cases where we're making independent choices, we get quite a lot of possibilities, because any combination of choices will do. So if you have independent subproblems, where it doesn't matter what you do in each of them, you take the number of ways you can solve the first one, the number of ways you can solve the second one, and you multiply. Because you get so many of these combinations of, like, oh, maybe I'll choose A from this and B from that, maybe I'll choose A from this and C from that. But you pick and choose different bits. Could you give examples of each? So this diagram up here is supposed to be, the reason it's laid out like 4 and 6 rather than 5 and 5 is supposed to be that it's showing you these are the ways where object n plus 1 is paired with one other element. There are choices about how you do that, and then the remaining elements, n minus 1 of them, are also partitioned up. With 3 objects, there's only one way to do that, so it's not very clear what's going on in general. But maybe I'll draw a picture to try and explain what's going on in general. Let's zoom into case 1. So if we pair n plus 1 with something, we get a choice here, and then our challenge is to partition everything else. So I'm going to put a box here labelled everything else. And there's lots of ways that we might partition things inside here. So I'll try and do different rows to illustrate that there are different ways that we might partition this. The number of sets that we use is fixed, because we've used 1, and there are now k minus 1 sets to use here and here and here. We want k of these things overall. For f n plus 1k. So we get a choice about which element is actually appearing here, and then we get lots of choices over here. So something like choices, we have n choices for what's to put in the question mark, multiplied by loads of choices for how to partition the other stuff. Everything else here is n minus 1 other elements. So we know that, well, we know that it's quite a lot. In fact, we have a name for how many that is. It's something like this: f n minus 1 k minus 1, where I'm subtracting 1 not because of a particular rule, but just because I'm thinking really hard about how there are n minus 1 elements still to do in a partition, and there are k minus 1 sets that we're putting them in over here. Our plan is that the number of choices in this first case is to assign something to this spot to be in a special 2-element subset with n plus 1, and then partition up everything else. So for n equals 4, this could be one of the things from the left column. For n equals 7, so something more exciting, like n equals 7, this would be 8 paired with something, and then partition everything else. Which could be like 1, 2, 4, 5, 6, 7 into 2 subsets. But there's other ways that I can split up the remaining numbers into 2 subsets. Loads of them. There are 6 things going into 2 subsets. So kind of all the possible ways to do something a bit like this. Remembering that I have to put at least 2 things in each subset. Okay, fun. That's the first case. Let's look at the second case. Second case is something like take an allowable partition of this and add n plus 1 to one of the existing subsets. So an allowable partition like this uses k subsets. There are loads of those. Loads of them. There are, well, let's be precise, there are, if you're doing a partition with this many things, fnk of them, because we're doing a partition of these numbers 1 to n into k subsets and just chucking in the element n plus 1 into one of them, into one of the subsets. There are also, well, there are k of them. So let's not get carried away, but if k is like 3 or something, then the choice of where you put n plus 1, you can choose which one you put it in. So we've got multiplication in this case as well. We've got fnk for the number of partitions, and I'm multiplying by k because you can choose which one you add it into. I think. Is that fair? Yes. The column on the right there with 6 things in is illustrating that we can take something like 1, 2, 3, 4. These are the partitions. These are the ways to partition the numbers from 1 to 4 into k subsets. Here it's 2 subsets. Commas between the numbers. And then in each case, for each of those partitions, you can shove in the number 5 into one of the subsets. You can add it in here, 1, 2, 5, or you can add it in over there, 3, 4, 5. So in each case, you get these 2 possibilities about where to put the new element, number 5. Which of these subsets you're going to get in. So you see, this is quite naturally 3 times 2. because there were 3 ways to partition up the numbers 1 to 4, and then for each of those, well, you've got a choice about where you put 5. Do you join it in with 1 and 2, or do you join it in with 3 and 4? So in general, you could put the numbers 1 to n into k partitions, and then you've got k choices about where to put the new element in. So we're almost there. My final answer is to add these things together. You've got choices. I need to do one tiny bit of work here just to convince you that these really are mutually exclusive cases and there is nothing else. But we haven't missed any. And I suppose I should convince you that they're mutually exclusive, right? That they don't overlap. Which is something like, there's a comment here about subset of size 3 or more. In the first case, the element n plus 1 ends up in a subset of size 2. In the second case, it's all of the ways where n plus 1 might end up in a subset of size 3 or more. Said differently, if you take an allowable partition and you consider removing the element n plus 1, crossing out the 5 from here, then either you get an allowable partition, which you would have discovered by that second method on the right, or you don't. The reason you don't is always that you removed something and now that element is now that subset is too small, which means that the thing you removed only had one friend. It was only paired up with one thing, which is precisely what the first case is. So that's the pairing. Those are the things that go together. This is mutually exclusive. So lots to do here. To think about the separate choices. Think about why those separate mutually exclusive choices are mutually exclusive. That the element 5 either appears with just one friend or with lots of friends. If it's got lots of friends, then removing the element 5 would give us some partitions that we've already thought about, so a kind of smaller problem. And if it only has one friend, then, well, there's not many possibilities of what that friend might be, and everything else is going to be partitioned up as well. So partitioning up, in this case, 3 things is a much easier sub-problem. That's what relations like this give you, a way to break a complicated problem into smaller problems. Right, I'm pretty sure I've got it right. Going to double check just in case I'm out by 1 anywhere, because that is exactly the sort of thing that happens to me when I do maths live. If you're playing along at home, there's a request for me to just change question, which is fair enough. If I'm not making sense, please say something. I know I said that about interviews, but I do also mean that for this. N times, yeah, cool, I'm good. There is some calculation to do. It's not very exciting. So to actually calculate f7.3, off you go, start plugging in things like 6 and 3. You'll need smaller values, oh my goodness. You could work them out from the bottom up or from the top down, it's up to you. Top down meaning put large numbers in and see which ones you want. If you put 6 and 3 in, then you discover that over here you get 5 and 2. So we already have that one. And oh no, what's this? 6 and 3 or something, so you've got to do more work. If you build from the bottom up, you start by thinking about f11, which we already thought about, and then see if you can derive f21 and build your way upwards. Either's fine. If you're giving it to a computer, building bottom up is probably better. Unless you're very good at getting your computer to keep track of which cases it's already calculated via some sort of lookup table. Anyway, never mind. You don't have a computer. You're doing this yourself, but I'm skipping it. Formula for 2n, n is to get you to think about the problem at the start again. So very particular case. We could go and use our recursion relation. It's a bit fiddly, I think. It refers back to previous values. So I think you can plug this in using the values 2n and n. If you plug that in, then it kind of refers back to previous values, and I think you can bundle it back down to talking about the previous, f of the previous thing, right, in this sequence as n changes, making this first number 2 less than the second one 1 less. It's a bit strange, isn't it? Because n is now in the second position rather than the first position. It's talking about putting 2n objects into n subsets. So that sounds hard, so let's stop and think. What does this mean? And what it means is to put 2n elements into n subsets, all of size at least 2. But then you realise that, hang on, if I'm putting 2n elements into n subsets, just like in part 1, that's only just enough. So they're all going to be paired up. And that's a much easier problem to think about. If they're all paired up, then, right, who's being paired with whom? Yes. Okay. Not improving, struggling with time and noticing tricks. That is just something that, just something I've got better at by solving more problems, and I think getting a little bit more into the kind of understanding what level of stuff I'm expected to do. So as you get used to a particular style of exam, the main reason you do past questions is to try and get a sense of what are you expected to do in this test, how hard is it, which helps you out. For example, this counting problem is something like now like, I think I've seen this one. I think I've seen this somewhere before, but it's this idea about like putting them in pairs, but then remembering the tricky thing is that the order of the pairs doesn't matter. The order within each pair doesn't matter. It's stuff like that, which I've seen before because I've done combinatorics kind of counting problems, because I've just been messing around with choosing things and things like that. The question we saw a while ago that was quite hard to do with, this is to do with choosing, this idea that I think the question was to look for the coefficient, the hard bit of spelling, coefficient of, what was it? It was something like x cubed y to the 5. So the question was asking for the coefficient of that in this expression, and that's also an example of some choosing, or choosing from brackets. So sort of that thing where experience of other bits of maths can make you better at, because maths is quite related. So having done a thing like that. So now I'm thinking, the order of the xy's doesn't matter because the multiplication is going to work out. That it doesn't matter if I see, this or I see this coming up when I multiply out all the brackets. The order doesn't matter, so I just want to choose things and then count how many choices there are that do that. Something like that. Yeah. Okay. 2 things in chat. One of them says, appreciate the live streams. Thank you. That is what I needed just now. And somebody else saying, do you think it's worth doing past papers since the syllabus change? Syllabus change was back in 2018. We have looked at past papers before that. There are some notes on the MAT website. Here, the upper page, this link, but without live at the end. The MAT page on the Oxford MAT website, it's got some notes about past papers. I think it's fine. I think you occasionally you will accidentally read a question about the trapezium rule, which depends really how you feel about the trapezium rule. The trapezium rule is one of the things that was removed from the syllabus for context there. Because it was removed from the A-level syllabus at about the same time. I think it's still good for you to look at those questions. I mean, we did on the live stream last week. Right, okay. Eva says, what's recursion? Recursion is where you relate a problem back to previous versions of the problem. Ideally, it's that kind of looping behavior, something that's self-referential, if you like. This equation is a bit self-referential because it has f on the left and it also has f on the right. It says that values of this function are equal to, oh no, some combination of other values of this function, with multiplication and addition in there. So it's recursion because it's a kind of reference back to the other values of the function. If you Google recursion, it just goes around in the loop. It just says, did you mean recursion? Which then loops you back around again. Ideally, your recursion doesn't do that, and your recursion relates tricky problems back to easier problems. As an exercise, you can use this to find f73 by plugging in numbers. This is true for all n and k greater than 2 or something, you can plug in values of n and plug in values of n and k, and you get these relationships between the values of f, which let you work out f7(3) without actually having to write down any subsets of size 7 or whatever, which is nice. People are ranking on 5. You can use the formula for 3 and 5. That's probably true. It's probably true. I like this idea of permuting the elements, to just think about shuffling them around to do the pairs. You know, I like to think about the, you know, so these lists with pairs in looks something like lists of numbers, but then these ones count as the same or something, because if I put the brackets around, that subset 4, 3 is the same thing as the subset 3, 4. Order doesn't matter within these subsets. But that's not too bad. We know how big the subsets are. Then you remember that the order of the subsets doesn't matter, so this is also the same thing. And so is this, and then that's a little bit harder because you remember the order of the subsets doesn't matter. So here I've done a lot of overcounting, which I can correct for, in that style that when you do combinations and permutations in school, you overcount and you allow for the amount of overcounting that you've done. N factorial divided by some stuff. So the order of the subsets doesn't matter, and the order within subsets doesn't matter. Sorry for the handwriting. Okay, if you have a gap year, are you expected to perform better than that? I think so. If you take a gap year, then you'll do the maths. If you apply the year after you've finished A-levels or equivalent, then you'll have finished A-level, you'll have maybe some spare time to do lots of past papers. You'll be a bit more prepared for the whole experience. You might have already applied to university, you might have already applied to Oxford, so you might know more about what's going on there. I don't know. I think it's reasonable to say that you might do quite well on that. Let's find out. There's a question about G in chat. I'm going a little bit off the vote. How long have we got? We've got about half an hour. Can have a quick look at the vote. You've maybe noticed that in order for me to review the results, I have to switch the vote back on. Let's run the vote for a little bit. Let's just have the vote on. There's the vote on the screen. There's 4 and 5, but then lots of votes for 2 as well. And then 1G did get a lot of votes for a short question there. Oh, 2 is fine. I don't have very much to say about 2, except it's one of these ones where you're asked to prove things and disprove things, so that's fun. Something you could do in questions where you have to explain stuff. Show that the student's guess is correct. The student's got some guess or something. In this case, the student's guess is wrong. So you can kind of prove and disprove things. To disprove something, we've seen one technique where you suppose that what they're saying is correct and show that nonsense follows. Sometimes it's even easier than that if the thing you're trying to disprove is a very general statement. If somebody says all bears have spots, then it's fine to, you don't have to enter that world and say, well, if all the bears have spots, then we wouldn't be able to tell them apart from the cheetahs, and that's confusing. So that would be not the real world that we live in, where we can tell apart bears and cheetahs. You just have to find one bear that doesn't have spots. It's much easier if somebody's made a big general claim. And this student has made a very big general claim. Look, it's got for all n, for all positive integers k. Wow. So if they're just wrong once, then you could prove them wrong just by finding a value of k where they're wrong. Actually, in this question, it's a bit easier to use the maths that we've done so far to talk about what happens eventually. But if somebody makes a big general claim, you can prove it wrong just by showing one counterexample. Here's a bear, no spots. You're wrong. Right, okay, the additional voting time hasn't totally helped, except people have now voted for 7, which I didn't see coming. So what we're going to do, we've got 25 minutes. 5 minutes on G, 5 minutes, really quick look at question 1G, and then some question 7. I'm just not sure I've got anything clever to say about question 2, other than, yeah, you can multiply out this. You can work out the sum of the first k numbers. Eventually stuff happens. Okay. Let's see what we can do over here in 5 minutes. Here we go. Right, I don't know why I've set such a crazy sort of time limit. I will see, it will be fun. So we had a question like this last week, or maybe the week before, where we had a system of equations. I think it had logarithms in, and we were asked whether it solved things uniquely. It was all 3s and 5s and 16s, and the number 4 was relevant in the end, but yeah. So it might be the case that this has a unique solution. We're told that these are positive numbers, and they satisfy all these equations. Might be the case that we're now done. This specifies A, B, and C uniquely, or it might be the case that there are no solutions, or something in between. That some of it is specified, like maybe C is specified uniquely, but we can't work out what the values of A and B are. Fair enough. One of the first things I want to do is to convert these logarithm statements into power statements. Power statement is not really a phrase, but I think you know what I mean. Exponentiate both sides. Good. So then I kind of want to see what the consequences are. So I guess I'm doing an if then. Say if these are true, then I sort of want to start eliminating things, don't I? Something like, I can see these first two have both got powers of C, and they have A's and B's in. So I think my first guess is to sort of plug in this B equals, maybe I should put the B over here. No, because that'll make if I plug in the B up here, I'll get some sort of horrible power tower. I've played with power towers before, they're hard work. You have to keep remembering to draw brackets around the thing upstairs in the power. I don't want to do that. So I'm going to plug it in over here instead. And I suppose this looks like a power tower, but in fact it's not a power tower because rules of indices tell me that this is just a to the power of c squared plus 3 over 2c. You get to multiply them in this case. A to the m to the n is equal to a to the mn, where my big pause was for closed brackets, which I drew on the board. It's easier when you have it written down, isn't it? Out loud is not a good way to do maths. Anyway, I suppose that what I'm now saying is that a to the power of 1 is equal to this thing, which is starting to look a lot like I'm finding the value of c. Can I compare the numbers up here? Well, if a is not 1, then yes, I can. If a is 1, then I'm very suspicious about this logarithm over here. Maybe I should worry about a equals 1 separately. I'll go and think about a equals 1 in a minute, and I have only got a minute. Yes. Ooh. Maybe plugging in over there was better. Chat is doing a different strategy. Go on, maths 222. I don't totally know what you've done because of a sort of lack of brackets, which has concerned me greatly. Have you plugged it in the other side? No, don't know what you've done. Sorry. So I compare the exponents. Do I need to worry about negative numbers? No, I don't, because everything's positive up here. That's a quadratic. Can I just solve this quadratic? Sure I can, probably. I think it's probably got nice roots. Why do I think that? I've solved a quadratic like this before. I have like 2 and minus a half. I think. Multiply to minus 1 and sum to 3 over 2. So C is 2. C is not minus 2. C is 1/2. This is getting there. Not that one. Okay, if C is 1/2, then A is B squared, B is A to the half. That's very nice. And also separately, I haven't looked at this equation yet at all. So take this one over here, not quite over there because that's behind chat, but bring this one over here, and this is something like A is equal to 1/2 to the power of B. And also I know that A is B squared. So I've got this weird equation. On the one hand, I know that A is B squared, which I've not quite formed very well there. A is B squared. On the other hand, it's half to the B, which is some sort of decreasing line, like this, different color. Some sort of decreasing line. Ooh, half to B. And I've just remembered that both sides, both these things are positive. So I think there's a unique solution in there. I don't know what it is, but half to the B comes down, B squared goes up. So unique solution for B. I don't know what it is. Then A is B squared or something, which is unique. So I'm starting to think that this has got a unique solution. Overall, I just need to worry a little bit about A being the number 1. If A is the number 1, then B is 1 to the C is also 1. These things are bigger than 0, so no powers of 0 kind of confusion. And B 1 to the C is also 1. And then I look to the other one and I see that 1 is C to the 1, so C is also 1. And now I have to think very carefully about the middle equation, which would say that 1 is 1 to the 5 over 2, which it is. Oh, so do I think maybe that log base 1 of 1, I don't really like log base 1 of 1. Yeah, I don't really think that's 1. I don't think log base 1 is defined. Can I get around these? Yeah, so all the things on the left would be log base 1 of 1, which we would then be claiming. Maybe you think this thing is defined. I think it's not defined. Surely you don't think it could be 1 and 5 over 2 at the same time, if it means anything. That the powers work out, but the logarithms really don't. It's a strange wrinkle. When you do the switch from powers to logarithms, you're sort of assuming that the logarithms actually make sense. Cool. Same equation eventually. C is 0.5. Yep, I've got that down here somewhere. And then the other one's very hard to solve, but you probably can't solve it. But there's only one point that satisfies both of these equations, where this one says A is 1/2 to the B, and we separately know that A is B squared. I've got two facts relating together A and B, so I've drawn these pictures of 1/2 to the B and B squared, which have helped me realise that, well, B squared starts at 0, increases. B to the 1/2 starts at 1 and decreases. There's one point where they cross, which is, I guess, my solution. That's the value of B, where B squared and 1/2 to the B are the same thing. So I guess I label this picture like this is A, this is B, or something weird, but whatever. At the coordinates where they cross. And I don't know where that is, and I also don't really care where that is. Good. Okay, so I think it specifies these points uniquely, unless you believe that log base 1 of 1 makes sense, is equal to 1, and is equal to 5 over 2, which I don't think anybody does believe all three of those things. So, fair enough. In which case you can't pick any of these options because you're in the position of specifying A, B, and C as two different sets of values. So I guess you probably eliminate that one and pick A anyway. If you did this question in 2019 and worried about log base 1 of 1, then I hope you didn't worry about it too much. I think I've already worried about it too much. Good. Okay, that was 5 minutes on. Well, that's more like 7 minutes on question 1G. Let's bounce to, what did I say I would do? Yeah, log base 1 of 1 is not good. I can't remember what I said I would do. Was it 7? Did I say I'd do 7? Doesn't seem likely. Did I say that? Oh, look, I can view the results without turning it on. No, I think I did say that. Right, okay, then we're doing 15-20 minutes on question 7. Ah, it's an experiment with boxes. Electronics, not really though. I'm going to turn chat off just because this question looks like it's got a lot of writing. Okay, I remember this. I thought about this question quite a lot in 2019. Two identical black boxes. They've each got a large display in digits. Okay, two buttons marked A and B. A is a reset and B updates the display using a complex but unknown but fixed function. So you get to see this sequence, which is defined by some function that you don't know and probably aren't going to be able to work out, and we're going to apply it lots of times. And the display has too many digits for you to remember more than a few displayed values. Okay, you can compare the displays on these two boxes. I have two of them. Okay, good. Count the number of times you press each button. And this is just, so this first bit about you press it and the sequence is going to repeat. The sequence repeats because there are only n digits on the display. So eventually this sequence is going to get into a loop. I think that's the point of these next parts of the question. Well, then you keep pressing. So same behavior on pressing the buttons. And then there's going to be a lot of stuff here to talk about how you end up in a loop, precisely a loop. The sequence will eventually has to have the same number twice, And then as you keep pressing the buttons afterwards, you see the same stuff. So let m be the smallest number such that xm appears more than once in the sequence. M is the index here, the smallest number such that xm appears. So m might or might not appear in the sequence. Xm is the thing that appears in the sequence. P be the smallest number such that you see it again because it appears more than once. Yep, so first thing you see. And then this argument is going to be that pressing the button, pressing P times is a fixed behavior. So this question was not for math students, and someone in chat is not happy that I'm talking about it, or they're questioning that we're talking about it. But I think I'm answering a previous question, but is this question helpful for preparing for maths at university? I think it is, because look at it. It's about sequences. It's about inevitable behavior of sequences on a finite space, which sounds like maths to me. Good. Okay. So this thing says pressing it p times is fixed behavior. So going up to I plus kp means you've hit it p times k times. It's k times p. So hitting it p times gets you a repeat. And doing that process is also a fixed behavior. So doing it again gets you back to the same value again. Okay, where are we going? I mean, it doesn't get much more maths than this, does it? This is definitely maths. I'm going to label it with an exclamation mark. There's inequalities and everything. Given numbers I and j, I strictly less than j, so this one happens first, and then later you see xj. Oh no, show that these things are equal if and only if I is greater than m, and I think this is referring back to the things in the previous part of the question, and j minus I is a multiple of p, and there's a hint on this, to let r be the remainder on dividing j minus 1 by p, and argue that r is 0. Okay, so I'm going to follow what it says. I'm going to say let j minus I be kp plus r with some remainder. So that's dividing it by p, getting some remainder. Remainder r is between 0 and I guess it could be as large as p minus 1. Okay. I guess it has this property that is between 0 and p minus 1. Could be 0. Won't be p minus, no, it won't be p, so it could be p minus 1. What do I want? Well, xj is equal to xi, and I'm going to write something quite complicated about xj, because I know that xj is something like xi plus kp plus r, because I can move this I onto the right hand side. I plus kp plus r, which is then the same thing as xi plus r, because pressing the button p times gets you back to where you were, pressing it kp times. Yeah. So this is using part 3 with I plus r instead of I, but that's okay. Okay, said differently, this is something like to get from xi to xj, you had to press the button quite a lot of times. You pressed it p times, maybe, but that doesn't do anything. I'm going to get back to where it started. So all of the times you maybe pressed it lots of times, but if you pressed it p times, that was stupid because you got back to the same number again. So don't do that. Maybe do if you like, but there'll be some remainder, and it's the remainder that we're interested in, because that might change the thing. So if that gets back to the same thing, then you have a situation now where, oh my goodness, this this distance xj is xi plus r, but r is less than p. So you found two values of the sequence that are the same, even though they're really close together in the sequence, xj and xi plus r. Oh yeah, we know that this is xi is equal to xj. We're given that xi is equal to xj. Sorry, so xi is now turned out to be the same as xi plus r with a tiny remainder. You start at xi, you do lots of presses, but it's the remainder that matters. So forget about the times you did lots of kp presses. It's the remainder that matters. So what we've discovered is you start with xi and you press it r times a small number, and you saw the same value. But now that means that it's going to repeat on this shorter period of sequence. It was supposed to be the case that this was the p bigger than 0 was the smallest number such that this thing repeats like this. So it must be the case that the remainder is 0, that actually you haven't pressed the button, or you pressed it a multiple of p times, the thing we were already thinking about. We had this word smallest up here somewhere, which means that you can't have r less than p. You can't have it repeating faster than that. Gosh, anyway, back to the boxes. I do my letter, long story. I do the letter P like this because of my fluid dynamics background. It is a long story that I don't have time for immediately because I am, for some reason, trying to do question 7 on that. I'm going too fast. How do I know the division would give kp? I suppose some multiple of p is what I mean. When you do division, you get to choose what you're dividing by. I'm trying to say I'm dividing by p. There's some multiple of p in there and some remainder r. And the multiple of p doesn't matter very much because in this question, p is such that when you press the button p times, you get back to where you were. It's a bit strange. These first 4 parts of the question are trying to justify something that I just said as an offhand comment, right? That the behavior of the button is a well-defined function behind the scenes. We don't know what it is, but it's consistent behavior when it sees the same input. The place we've got to, after these first 4 parts of the question, is that after a while it gets in a loop. And it did the loop. At some point, it did the loop for the first time, and we can kind of identify that's well defined. It didn't, I suppose, it didn't do a short loop and then do a different sort of loop later on. Once it's done a short loop, it's now stuck in the short loop. So once it's looped, and the way you might explain that is something like the first time you see a repeated value, you now know what it's going to do. And you know exactly what it's going to do. It's going to do maybe fun, interesting values, but then as soon as it repeats a value that you've already seen, it doesn't have to be the first thing you started with, but as soon as it repeats a value you've already seen, you now know its behavior exactly. And the first 4 parts of the question are trying to walk through that very precisely. But I hope it makes sense to you that at some point the mysteries of the button, as you press it, you'll see weird stuff, but it can't keep surprising you forever. There's only finitely many things it can show you. And as soon as it shows you something that you've already seen, your interest in the button is now, it's now a solved thing, right? You know what's going to happen now. You've already seen this. It's going to happen again. You might not have a memory for all of the many, many numbers it can show you, but in some sense it's kind of well-defined behavior from now on. The question is to discover the values of those things using 2 boxes. So if we had 1 box and a perfect memory, we would just keep pressing until we saw one of the many, many, many things we'd already seen. This turns out to be a little bit sort of inefficient if you're into computer science, or if you're a mathematician, it turns out to be really boring to keep track of loads and loads of numbers that you've seen, waiting until you see one of the many, many numbers you've already seen before. There's a way to use 2 boxes in parallel to work out these things. The description in part 5 tells you how to do this. It tells you something related. So you press button B on one box and button B twice on the other box. So you don't keep track of the numbers that you're seeing. Who's going to remember all of those? But you press button the first box once and the second box twice and compare the displays. And after a while, you will see, we're going to prove, the same number on both boxes. You've kind of got one of them going through the sequence twice as fast as the other. So there's some relationship here. If you know that eventually it's going to get to a point xm, let's draw a little diagram. You'll see these things here to here to here. These are maybe states, numbers that you'll see. I'm drawing little circles for my numbers. but eventually it starts to loop back around again, and you'll see something you've already seen, and then it's stuck in a loop. Now it's going to go around again and again and again forever. It's stuck in a loop. If you have one of the boxes going twice as fast as the other, eventually they'll both end up in the loop. The names for these things, this is xm, the first thing that repeats, and p is the length of of this loop. How many presses you have to do to get around the loop. So you might see some weird stuff, but then eventually you'll see something you've already seen, and then it loops. So something like the one that's going ahead will see advanced values, won't it? So what do we know? We know that P must divide. We know that so 2u. So if this ever happens, it's the case that 2u minus u is a multiple of P. We know that from part 4, which means that u is a multiple of P. I can't immediately see what it's got to do with m. Smallest. Yeah, Anna's out. Somebody says, OMG, this question looks so hard. Yeah, the question's pretty tough. Use a multiple of P, is that enough? Can I say anything else about m? Probably not. Because it might be the case that the loop is very small and m is very large. So this could happen straight away when m is u, or it could happen if the loop is very large. The loop can't be larger than m, so p must be smaller than m or something. Kp, because it might have gone around multiple times. Goodness me. Am I being stupid? I just think it's just a multiple of u. Oh no. There's more. It's got to have entered the loop for both of them. Oh, I've missed this bit here. I is going to m. Where this other part of part 4, I has to be greater than or equal to m. So for this question, we would say that u is greater than or equal to m. It's going to be the least such number that's greater than or equal to m, such that u is a multiple of p. Right. Okay. And then there's 2 more parts to actually work out the values of m and p, but I'm getting the sense that people in the room do not really want to do all of this question live on the MAT livestream. And I'm also running out of time. I think I can be more helpful by actually reading chat and stuff. Okay. If you want to look up the solution for how you actually deduce m out of this, which involves something like working out, okay, you know that it's going to loop eventually. You're bound on how long that's going to take, because you've seen these screens agree. You know that m is not as big as u. So maybe you could send one of the boxes off ahead or something. You could do something like that, couldn't you? You could send it ahead by u steps. Maybe that does something. Yeah, so if you give one of the boxes a bit of a head start, I think you can then use that to see how long it takes before they start agreeing. Yeah, so once you know u and m, for example, you know how long it is until they start repeating. So you could press both the boxes m times to get them ready to the start of the loop if you know m somehow, and then hit the second one and count how many times you hit it before it gets back round again, and compare the screens. So your 2 machines there help you to remember the value at the start of the loop. How do you get the value of m though? Nope, stuck, don't know. And chat at the moment is just talking about me missing a big block of text, so we'll leave it there, I think. How would you actually go about doing long form questions and never make a mistake in the middle that fumbles everything? I'm not sure I fumbled everything. I think it's an overstatement. For example, just there I was imagining what I would write for the last part of the question, even though I've got a bit stuck on part 6 and a bit bogged down in all the details. What did Callie say for this? Callie, who's a second year student, having the right idea method gets you credit. Yeah, even if you don't fumble things. Someone says, hey Matt, which I think means I need to clarify that my name is not Matt, but you know, never mind, close enough. Talking about maths in Oxford and Cambridge, they're both great universities. They both have great maths courses. If you're in the position of choosing between the two, then it's a pretty good position to be in. Totally different admissions processes, and one of them has Saturday lectures. It's Cambridge. Cambridge has Saturday lectures, or at least have done in recent years. Who knows what they'll do in the future. Okay. Yeah, you head start and compare, and then it gets in exactly when they've done a loop. Huh, that is weird. Yeah, it is a head start by you. It's the thing I mumbled out loud. Okay, cool. Right. Good. Anyone else? Eva's joined for the first time. Good to see you. If it was also your first time watching MAT Livestream, sorry about this mess. And I think it's the first time I've refused to talk about a question. I didn't talk about question 2 at all. I switched and talked about a different question. Nothing wrong with question 2. Just didn't feel like I could say anything for it. Oh, goodness me. Right. I think it's time for me to go home. First time watching live rather than recorded. You get live, you can't skip. It's the thing about watching live, you can't skip. You can tell that I'm going to do a car crash of a thing, and you can't fast forward. You also can't watch at double speed. If you've been watching this at double speed, then see you next week. We'll be back in 166 hours for another episode of the Oxford MAT Livestream. I've been James. If you have questions outside of the live stream, there's a contact email address in the YouTube description or on the MAT Live page. If you scroll all the way down to the bottom, you can contact us or pick up from somewhere on that page the contact address for undergraduate admissions, which please do get in touch if you're having any trouble with your application, registering for MAT, or if you're having trouble getting a teacher's reference or something, then yep, get in touch. Good. Right. Okay. Take care, everyone. See you next week. Bye.